Okay, so the recording has started, so we can begin. Hello everyone, and thank you for joining. I'm Evangelos Yfantidis, current chair of the SECED Young Member Subcommittee, and today I have the pleasure of welcoming you to our lunchtime webinar on advances in estimating seismic responses of steel frames and rocking structures. Before we begin, please let me go through some housekeeping rules and important information. I will first kindly ask you to keep your video cameras off and microphones on mute for the duration of the presentations. Just to clarify, this is applicable only for the audience, so I would like to invite the speakers to keep their video cameras on while presenting, if that's possible. After our speakers finish with their presentations, we will have some time for a Q&A session. But in the meantime, please feel free to type any questions you might have in the chat. Please also note that this webinar is being recorded and will be later uploaded on our SECED YouTube channel, and therefore, by dialing into today's event, you consent that any views or information you share will be made public. I would also like to make a quick announcement. Every year, SECED runs a funding scheme called the SECED Fund, where we award up to £1,000 to individuals or teams who are seeking to further their studies, research, or career in the field of engineering dynamics, or they're undertaking a project that will promote or lead to advances in this field. We consider applicants of all nationalities with a valid SECED membership, and there are no restrictions on academic or employment status, as well as there are no age limit. The SECED Fund 2024 is now open, and the applications will close on 31st of July. So if you're interested, you can find more about this on our SECED website, including the required application forms, as well as terms and conditions for applying. I will shortly paste some relevant information in our chat if you're interested to find out more. Now, moving on, I will introduce our three speakers for today. Our first speaker is Dr. Christian Malaga, an associate professor, senior lecturer at Imperial College London, where he leads the earthquake engineering and applied dynamics research areas and heads the emerging structural technologies research group. His publication record includes more than 80 papers in topics related to earthquake engineering, computational modeling, and AI. His work has been recognized with multiple awards, including the Chong-Gun Sei Research Award from the Institution of Civil Engineers, the Structures Best Research Paper Prize from the Institution of Structural Engineers, and the Unwin Prize from Imperial College London. Christian also serves in several committees related to international code development and the advancement of engineering practice, and is acting as a specialist consultant in related areas. Our second speaker is Faridah Zahra, a doctoral researcher in the Emerging Structural Technologies Research Group at Imperial College London, currently working on the development of hazard-consistent models for steel frames using mechanistic and data-driven techniques. She holds an MSc with distinction from the University of Aberdeen in the UK and a bachelor's in ocean engineering from Institute of Technology Bandung in Indonesia. She has over 7 years of experience carrying out structural analysis in several industrial projects in Indonesia. Our third and final speaker is Yixuan Zhang, a doctoral researcher in the Emerging Structural Technologies Research Group at Imperial College London, currently working on the optimization of the design of rocking timber structures and their large-scale testing. She holds an MSc with distinction from Imperial College London in the UK and a bachelor's in civil engineering from Southwest Jiangdong University in China. Now, without further ado, I will hand over to you, Christian, to start with the introduction of our talk. Thank you very much.
Thank you. Thank you very much. I'm just starting to share my screen. So I'm not going to take that long. My job here is basically to try to introduce and produce and give some background to Yixuan's and Faridah's presentation. As Evangelos mentioned, I am leading the Emerging Structural Technologies Research Group. I'm a faculty member here at Imperial College London, and I lead this Emerging Structural Technologies Research Group, where I have the opportunity to supervise very bright and smart doctoral researchers, and you will hear from a couple of them in a minute. So what we do here is basically conducting high-quality, curiosity-driven research that is focused on understanding and promoting innovative technological solutions in the field of structural engineering. So what we aim is to address some of today's greatest challenges using a variety of tools, analytical, numerical, and experimental. So we cover a wide range of structural problems and structural typologies, from the more humble to the extraordinaire. So on the left-hand side, you can see an experiment we carried out a few years ago in collaboration with Arup on the seismic performance of cane and mortar type of walls, what in Latin America is called bajereque, with the purpose of providing sustainable housing solutions for El Salvador. And this project went on to win a sustainability award from the ISTRAC-T. On the right-hand side here, you can see some of the more recent work we have done in collaboration with Greenwich and NASA, trying to provide optimal solutions for the shielding structures that will be protecting some extraterrestrial assets. And we used a number of AI techniques to do that and subject those models to Marsquakes and moonquakes and things like that. But throughout our research, we do, apart from the experiments, quite a lot of modeling, right? Notably in steel and timber, but also in other materials. And we cover different structural responses, a diversity of structures, bridges, buildings, and so on, different scales from the macro to the micro, from whole structural systems to the interaction between bolts and joints, incorporating blast, fire sometimes, and other forms of extreme loads. Detailed continuum models and also some form of stick frame models of systems. Now, modeling is an interesting beast in itself. It has been said by a statistician, and I'm sure many of you have heard this before, that all models are wrong, but some are useful, right? And what that really means is that the ability to set up an analytical or numerical model that can capture the important aspects of the behavior that we need to capture to answer a particular question is really the key in all this processing, this process of modeling. So today you will be hearing from two different modeling approaches. On the one hand, first you will hear from Faridah about her work on the provision of hazard-consistent comparisons for performance-based assessment of steel moment frames, where she's trying to answer the question of how much the disregard for the causal relationship that exists between the intensity of the earthquake and the properties, the characteristics of the ground motion, how much that affects our estimates and our predictions. And then you will hear from Yixuan on the challenges of modeling structures that have a strong nonlinear response, and some of his attempts to model a particular new type of device called the inerter and the clutch inerter in this particular case, through a framework that I think has a great potential to get us a bit closer to the truth in these non-smooth dynamics problems. So without further ado, I will let Faridah start speaking and presenting.
Okay, so can you hear me?
Yes, we can.
I will share my screen and okay. So, hello, good afternoon, everyone. I'm Faridah Zahra, and I'm going to present a part of my PhD with my supervisor, Christian Malaga, and my second supervisor, Jorge Macedo from Georgia Tech. So it is titled Hazard Consistent Performance Assessment of Steel Moment Frames. First, we will highlight why do we need a seismic performance assessment of a structure and the importance of a hazard consistency in the assessment, which is secured through method called conditional scenario structure, or CSS, in this study. So we all know that most of design codes are not performance-based, and the lack of evaluation or understanding of the actual ability of the design structure to provide its intended performance has been a challenge in the aftermath of many past earthquakes. So we have a question of how to build a structure that continues to function after a relatively more frequent small earthquake while still being safe if a rare severe earthquake hits. So this question can be answered through probabilistic seismic demand analysis within a seismic performance assessment framework that is widely known as the PRPBE. So intuitively, a performance assessment of a structure needs to be based on the hazard at the selected site, right? However, surprisingly, the available studies on seismic performance assessment were based on the hazard inconsistent assumption. So one of the main aims of the study is to stress the importance of having a hazard consistent assessment, which allows the seismic behavior of a structure to be linked to its expected rate of occurrence based on seismic hazard at the site. As mentioned, the hazard consistency in the study is secured to conditional scenario structure, or CSS, and the first step of CSS is representing the seismic hazard level at a site by the probabilistic seismic hazard analysis. And the study used the PSH result of a site in Oakland in California. And in the next step, constructed from the PSHA, UHS of the uniform hazard spectra is a commonly used target spectrum that assumes equal probabilities of exceedance of spectral acceleration at all periods. However, as this UHS is constructed from the PSHA, it constitutes of a composite of all earthquakes that take part in site-specific hazard care. However, these earthquakes are very unlikely to occur simultaneously, so the UHS is actually not representing a spectrum of any single earthquake, and none of the single earthquake is likely to produce a spectrum as high as that of the UHS over a wide range of periods. So Baker and Cornell developed the conditional mean spectra, or CMS, as an alternative to the UHS. The CMS represents the average spectrum that would occur if the selected spectral acceleration at the reference spectral period occurs. So the term conditional refers to the spectrum being anchored at the selective spectral acceleration at the conditioning period, T, and the term mean refers to the mean value of the response spectrum conditional upon the occurrence of the spectral acceleration at the conditioning period. And then the CSS per hazard level here is selected from a subset of a number of recordings from the suite of good motion that we have that is scaled to match the CMS and its variability for each hazard level. So this method ensures the recordings have the correct spectral shape, accounting for the peak to true variability of the good motions. As the result of the CSS methodology, so we have a set of realistic earthquake spectra with assigned rate of occurrence based on their spectral shape and intensity. And based on the PSHA of the site in Oakland that we have, this study selected 596 motion records, where each of them is assigned a rate of occurrence. And this rate of occurrences of this set of good motion can later reproduce the hazard at the site to prove its consistency. And as an example of case study to show the importance of hazard consistency of the analysis, a part of our study has performed hazard consistent performance assessment of 24 frames that were run with the almost 600 motion records from the CSS with the high performance computing facility at Imperial College London, resulting in more than 14,000 non-linear response history analysis. And then we assess the behavior of the peak, transient, and residual interstory drift as the engineering demand parameter of interest, and also assesses the several patterns found from this response database. And then we also developed prediction models for these EDPs based on this extensive structure response database. And the process of developing the model and the model itself has been published in a paper as presented here. And first, the results of the seismic demand assessment is presented in the form of inter-storage hazard curve, where here the annual rate of exceedance here on the y-axis as the inverse of return period of all level of inter-storage on the x-axis is estimated through the CSS. And then presented here also two horizontal lines to denote two performance level of interest based on FEMA P58, which is life safety performance level with 475 years return period, and collapse prevention performance level with 2,475 years return period. And then an inter-storage prediction model was developed in the study from the structural response database from the NRHA. It was preceded by feature selection with several machine learning algorithms to select the best predictor from the structural and the seismic parameters that we have. And then multilinear regression was carried out to develop the model. So it can be seen here with the markers that our model is well matched the hazard curve. And also can distinguish different hazard level where it results in higher demand at higher return period. And then this model was compared with the available non-hazard consistent deterministic models from the literature, and all other available models are found to severely overestimate the inter-storage demand, even beyond collapse, beyond 10%. And notably as well, the available deterministic approaches were also found to enable to discern between the different hazard levels. And then in another paper, we also assessed the residual drift demand, which is arguably more important than the transient peak inter-storage drift demand, as it is actually the structural response that is more practical to be measured in a post-earthquake assessment. And also, we developed the hazard consistent prediction model of residual drift. And as before, the assessment here presented in the form of hazard curve, and our model here is shown to well match the actual demand of the frame and able to discern different hazard levels. And the available non-hazard consistent demand from FEMA P58, on the other hand, severely underestimate the residual drift demand, and the model from available studies were found to overestimate it. And these available studies also cannot distinguish different hazard levels. While those studies are mentioned shortly, just to show the importance of hazard consistency in the performance assessment of structures, this presentation will focus more on a hazard consistent point of view of available seismic codes. So in the context of steel frames design, available seismic codes require these frames to respect certain maximum transient deformation levels, in addition to having a certain lateral strength under seismic loads. And these criteria are prescribed differently in different codes, right? So where number of differences are found between the current Eurocode 8 will from this point will be referred as EC805, and the revised draft of Eurocode 8 referred as EC823, and the American Seismic Code ASC 7. So one part of my thesis evaluates the seismic design rules in the current and revised draft of European and American seismic codes within the hazard consistent performance assessment framework, where it will answer the question of will a building at a certain site designed with different seismic codes result in similar structural performance, and will the seismic codes yield well-controlled structural design for all structures for a certain hazard level of a site. And several key differences are found between the design codes and their comparisons, but due to time constraints of this presentation, I won't be able to explain in detail. But the key difference highlighted in this study are their elastic and design seismic spectra, the inter-story drift limits, the capacity design rules, and the second order effects. In the next step, we designed a number of frames with each seismic code. And first, we designed the frames, a group of elastic spectra for the current Eurocode, the revised Eurocode 8, and the ALC7 were constructed so that they match as closely as possible to the Oakland spectrum from the UHF at 500 years in period for the range of structural period of interest. So two red lines here are presented to denote the range of a natural period obtained from the frames under consideration, as will later be shown in the design process. Here we can see that between this range, the spectra show a very good match with the site-specific spectrum for Oakland, and then these elastic spectra are then used for the following design process of the frames in the study. So the formula to calculate the seismic shear first in the equivalent lateral force method or ELF method for the design of the frames are different in the European and American code. And the spectral acceleration component of the formulation, which is the design spectra multiplied by a factor, is presented here in the right figure. So it can be seen that although the elastic spectra are made to be the same to describe a certain site within a certain region period, the design spectrum of each code are different in certain ranges. So based on the seismic first, the three families of frames are designed according to the current Eurocode, the revised Eurocode 8, and the ASC7. With different numbers of stories and different number of bays. So 16 frames are designed for each code, resulting in 48 frames overall. And so these frames were designed with the help of a tool called Automated Seismic Demand and Analysis, or AutoSDA, developed by Yixuan and Professor Burton from University of California for the ASC7-based frame design. And this Python-based framework was modified in the study to incorporate the European rules. The AutoSDA is a Python-based platform that automates seismic design that works by trying the biggest possible fill section for the frames and reducing those sections until they are optimized as small as possible based on satisfaction of relevant design constraints and also constructability constraints. And as expected from steel frames, all designs are governed by the drift. And here presented is the weight of the frames normalized against the weight of the current Eurocode frames for all 48 frames. So overall, the weight of the frames based on the revised Eurocode are slightly reduced from the current Eurocode here with the blue bars. And then the ALC frames, on the other hand, result in the lightest frames down to 46% of the weight of the current Eurocodes due to the last string and drift limit in the ASC7. And then all frames were modeled and analyzed in OpenSea. The frames were modeled following concentrated plasticity approach with elastic beam column elements connected by a rotational spring representing the potential plastic hinges at the beam column connection. And the panel zone here shows the detail of the spring models that is adopted that follows the bilinear hysteretic response based on the modified Ibarra-Crowin-Clare deterioration model. And then so after those frames are obtained, all 48 frames were analyzed with the almost 600 motion sets from Oakland from the CSS with the HPC facility. And then the results from this more than 28,000 analyses were used to develop the hazard curve for the performance comparison of the frames with different design codes. So as an example here presented the illustrative hazard curve of two frames with that were designed with different seismic codes as examples. It can be seen that both frames hold the same pattern where the current Eurocode frames have the lowest interstory demand, followed by the revised Eurocode, revised Eurocode 8, and then the American frames experience the highest demand. And then from this hazard curve as well, the associated maximum interstory drift at life safety performance level and the collapse prevention performance level for each frame are collected to be compared. So these values in this bar chart are the corresponding interstory drift demand of each frame. For example, here is the frame 1 designed by the current Eurocode, revised Eurocode, and the American codes for life safety performance level. And then we also obtain the corresponding demand for the collapse prevention performance level for all frames. Presented here as well in this chart is a horizontal line to mark the maximum drift limit for each performance level based on FEMA P58, which is 2.5% for the life safety performance level and 5% for the collapse prevention performance level. And all frames here are shown to be safely within the prescribed limits. However, one thing that can be seen from this graph is that codes of European and American codes are found to be unable to ensure a consistent demand at both performance levels. So, for example, here the current Eurocode shows that the interstory drift demand based on the current Eurocode vary between 1.3% to 2.2%. And then the ASE7 has the most inconsistent demand between 1.9% to 4.6% at this collapse prevention performance level. It is to be noted that it is desirable that code compliant design will result in a well-controlled responses where similar demands are expected at a certain performance level on all structures, depending mainly on the function as they're designed. And well, we keep all the things being equal. And so to compare between each code, it can be clearly seen that the current Eurocode takes a very conservative side, where the average interstory drift demand at life safety performance level is only 1%, which is 40% of the limit. And at the collapse prevention performance level, the average interstory drift demand of the current Eurocode is 1.7%, which is 34% of the limit. And then for the revised Eurocode, although the design rules in the revision have undergone many changes from the current Eurocode 8, the ensuing designs are still conservative. The average interstory drift demand for life safety performance level is found to be 1.2%. And 2% for the collapse prevention performance level. So these demands are very close to those with the previous one, the current Eurocode 8, although there are some considerable differences in taller frames. And on the other hand, the American frames have the most optimum design, where the average interstory demand at life safety performance level is 1.7%, which is 70% of the limit. With frame 16 here, with 12 stories, reaching the exact limit at 2.49%. And then at collapse prevention performance level, the average interstory drift demand of American frame is 3%, which is 60% of the limit, with the highest one here at frame 3, with 3 story at 4.6%. And then we also assess the residual drift demand for all frames. Here presented as before, the hazard curve of several frames designed with different seismic codes. And similarly with the interstory drift demand case, it can be seen that the current Eurocode has the lowest residual drift demand, followed by the revised Eurocode and the ASE7. And here presented the associated residual drift demand for life safety and collapse prevention performance level. The residual drift limit for each performance level based on FEMA P58 is also presented here, which is 1% for life safety performance level and 5% for collapse prevention performance level. And all frames are shown to have demand significantly below the prescribed limit. And again, nonetheless, from the perspective of the design rules consistency, the ALC is to show the largest variability in the demands, which where the residual drift demand of the frame can be as low as 0.26% and up to 2.4% at this slot suspension performance level. And on the other hand, the current Eurocode and the revised Eurocode consistently show very low residual drift demand, denoting that conservative design. So the cautiousness of the current Eurocode design can be shown by its very low residual drift demand, which is only up to 0.4% at the last French performance level, and the revised Eurocode demands also virtually the same as the current one in sort of frames up to 9 stories here. Noting once more that the changes in the revision of Eurocode 8 do not lead to significant changes in the expected structural performance. And the American frames, on the other hand, still have the highest demand at almost half of the limit here for frame 3, which is stories. And then, so in conclusion, from the first part of the presentation, we show that hazard consistency is essential to obtain meaningful results from our seismic analysis, and not considering the causal relationship between the intensity of the motion and its characteristic can lead to a severe misinterpretation of the actual seismic response. And when we compare our hazard substance prediction with currently available models, the massive under and overestimation associated with previously proposed non-hazard consistent models become evident. We have found differences up to 600% in response estimates. And then from the seismic code comparisons, we found that the drift demand assessment showed that frames designed in accordance with the current Eurocode 8 presents the lowest drift demand, followed by the revised Eurocode 8 and the ALC 7. In general, the current Eurocode 8 takes a very cautious stance with the average inter-story demand as low as 34% of the prescribed limit, and its newer generation, which has undergone rigorous changes in the design rules, is still on the conservative side, with an average inter-story demand at 40% of the prescribed limit. And the American code, on the other hand, result in the most optimum design, where the average inter-story demands are 70% for the life safety performance level and 60% for the class performance level. One thing to be noted as well here that when contrasted with our EDP hazard curves, our results highlight the inability of all mentioned seismic curves here to control structural response that lead to similar structural demands for all structures depending on their function on how they were designed at a certain earthquake resistance period. Okay, that's all. Thank you very much. I will listen here to Christian then.
Yeah, maybe Yixuan, can you start?
Thank you.
Thank you, Faridah.
Hello.
Hello.
Okay. Shall we start?
Yes.
Yeah. Hi everyone. I'm Yixuan, a second-year PhD student from Imperial College, and I will talk about the modeling structures with clutch inerter devices. Okay, my presentation will be divided into 4 parts. Firstly, I will introduce the inerters and the numerical modeling techniques, and the numerical model is then demonstrated by examples and its applications on a rocking structure. And then the last one is a conclusion. So let's start with an analogy between mechanical system and electric circuits, since they share the same differential equation. So in this analogy, the damper is equivalent to a resistor. Correspondingly, in the practice, we have velocity-based devices like viscous dampers. And the spring is equivalent to an inductor, And we also have displacement-based devices like yielding plates or frictional dissipators. And how about the capacitor? It refers to the inertia term of the equation. Is it equivalent to gravity mass? No, a mass has only one terminal. The real equivalence is the inertia, a novel device that can output force proportional to the relative acceleration of its two terminals. So the name and concept of inertia is initially proposed by Smith in 2002. After that, 2005, it was introduced into Formula One racing games by McLaren team. It is well known by public as J-damper. Unfortunately, due to its extraordinary performance, the use of inertia is banned in the game 2 years ago. However, earlier in 1970s, similar devices are already proposed and applied for protecting the piping system against impact in nuclear plant facilities. It has a different name called snoopers. The first prototype of inertia in civil engineering field is designed and tested by Arakaki in 1999, and until now, the real application of inertia in seismic control are still limited. One well-known example is the tuned viscous mass damper used in commercial building in Japan. So how does it work? In a single degree freedom system, we have its governing equation with additional term for the force from the inertia. According to the definition, the force is proportional to the relative acceleration, and the coefficient here is called the inertance of inertia. If we rearrange the equation, we find that the inertia directly modifies the mass term of the equation of motion. And how does the inertance come from? Usually, for mechanical inertias, the translational movement is converted into a rotation of a flywheel, just like here, the rack and pinion type inertia and ball screw type inertia. So the rotation, the translational movement will be converted into a rotation of a flywheel inside these kind of devices. And take a ball screw type inertia as an example. If we have a flywheel with radius of 10 centimeter and the ball screw lead of 1 centimeter, then the inertance will be 1,000 times of its self-weight, which means you get additional force without increase the self-weight of the structure. So it's way more efficient than the tuned mass damper. But there are drawbacks of pure inerters. Many studies revealed that the inerters can drive the structure as a power output, like a discharging capacitor. The inerter can only be effective when connecting to other energy dissipating devices like dampers. And furthermore, because it directly enhances the mass matrix, the natural frequency of the structure will be significantly shifted. Therefore, a clutch is introduced to allow the inerter to disengage with the structure. The clutch is passively working just like a mechanism in a bike free hub or a diode in an electric circuit. It will cut off the energy backflow. And it has been proved that the structure equipped with clutch inerter has faster attenuation during free vibration process. And based on the one-way transmission of the energy, it is feasible to construct a flywheel-based energy harvesting system. The energy will be stored in the flywheel of the inerter. However, the introduction of a clutch results in discontinuity of the system behavior because now the system have to switch between two states, the engagement state and disengagement state, and the transition is not smooth. Regarding to the numerical modeling, the numerical model need to be able to deal with that discontinuity. So our study focusing on the numerical modeling of the clutch inerters. So we have some existing methods, but they all have limitations. The first one is simplified sequential model. It is proposed when the clutch inerter is invented. In this model, the inerter is not explicitly modeled, actually. It simply assumes that the inerter disengages with structure when the structure is decelerating, and that the inertance of the inerter becomes zero. In the other words, for each new engagement after the previous disengagement, the structure engaged with the inerter with zero speed. Therefore, the assumption behind this is that the inertia will dissipate all the energy before next engagement. It is not it's not realistic. In case of a high-frequency structure equipped with very big inertia, this assumption means that the inertia need to dissipate massive energy within a very short period. It greatly overestimates the dissipation of the inertia. So we have a displacement-based contact model. It explicitly models the rotation of inertias involving additional set of equations and contact laws for describing the interaction between the structure and the inertia. But the problem is that the rotation displacement of the inertia monotonically increase while the structure is reciprocal. It is hard to obtain the displacement penalty contact between the two motions. To resolve this, we also have a velocity-based contact model. It uses dampers as a velocity-based contact element to model the clutching behavior. But they use discontinuous expression in the equation. And no matter the displacement-based or velocity-based contact model, they use penalty algorithm, which means the force is calculated by the penetration. This type of algorithm is unstable for the transient contact problem, like clutching behavior. In fact, most of the existing research focusing on the simple structure, simple system, single-degree freezing or multi-degree freezing. But what about 10-story buildings equipped with hundreds of inertias? So this is because lack of the modeling tools. Alternatively, we use mixed Lagrange formalism, which is proved to be very robust and efficient for modeling non-smooth behavior. I'm not going to get into the mathematics of this method, but just some general features. So MLEF is a flexibility-based method. In MLEF, we are going to solve two sets of equations, the equation of motion and the velocity compatibility equation. But the key is that we're not going to solve it directly. We solve the weak form of it, which is the optimization problem. And this optimization problem have a quadratic structure, which means it's convex. It's always convex. You can always find the global minimum of it. And that's how it's stable and robust. And the complex nonlinear behavior can be implemented by modifying the constraints of the optimization problem. And it also uses, because it's a flexibility method, so it uses Maxwell type element, which means all the basic units, they are connected in series. And you can model with complex series behavior with only one element. So based on that, we built a clutch inertia element in the MLEF framework. We start with the energy in the inertia by its definition and apply the mixed Lagrange differential with respect to both the global displacement and local force coordinates. The following expressions are obtained. And as you can see, there is additional term in the compatibility equation, which represents the deformation rate of the inertia. And moreover, we can modify this term to include a damping effect. And this finally ended up with an optimization scheme on the right, which is exactly the same as the original. This implies that the proposed clutch inertia element doesn't change the structure of the solver. And then I'll propose some example for the validation. To demonstrate our formulation, we use this single-degree freedom system, and on the right is equivalent model building OpenSys use penalty method for comparison. As you can see here, the response history, all these models, they agree with each other, and the sequential model exhibits faster attenuation due to its assumption. And you can see in the acceleration response, all other models have significant numerical oscillation except the MLEF. And here is the inertia hysteresis. the sequential model exhibits faster attenuation because the enclosed area in this hysteresis is larger than the real behavior of the inerter. And here is the clutch and inerter behavior history. As you can see here, the clutch force is also the clutch force predicted by other models also experience a very violent numerical oscillation. It means you cannot get exact result for clutch force, but that is very important for inerter design. The clutch force, to some extent, it decides the cost of the inerter. And furthermore, we want to know the proposed model should be able to handle a larger scale system. As we discussed, we compared the computational performance of MLF and OpenSea's model through this 10-story moment receding frame as a benchmark. This 10-story frame with lumped map plasticity with ideal elastoplastic behavior and twin clutched inerter are deployed at each story. The side column accounts for the P delta effect. And here's from the response history of the top story results predict by OpenSea's model and the MLF model. They generally agree with each other. We also did a convergency test for both models. We're focusing on the arrow of story displacement and acceleration. For the displacement, both methods are good enough, but there is a truncation for the OpenSea's model because the larger step will lead to numerical instability, and the model cannot converge, it directly crashes. On the contrary, the MLF allows using larger time step size with gradual increased error. And we're also curious about the efficiency of these two methods. We gradually increase the matrix size by increase the number of floors and check the total number of the iterations and time used. Although the MLF requires a bit more iterations in each step compared to OpenSea's, the MLF is more, but regarding to the total time used for the calculation, the MLF is more efficient in terms of the computational time. And before getting to the next example, I would like to introduce rocking structures. When people are talking about rocking structures, it refers to a structure whose base are not fixed to the ground, like what people did in ancient time. And nowadays, to enhance its performance, people used post-tensioning cables to provide additional restoring force. Why rocking structures are preferred? Because it releases the moment in the structure members, leading to less residual strains or damage, as you can see in the hysteresis curve. Therefore, it has other names called damage-free structures or self-centering structures. For low intensive earthquake, it behaves in the same elastic way as normal building, but in case of strong ground motion, it allows the base to uplift, and the dynamic behavior of the building will be dominated by the rocking mode, which is like a safety fuse. In this case, since the deformation is concentrated at the rocking surface, it provides a favorable location for seismic control devices like clutched inerter. The drawbacks of the rocking structures are obvious, that there is a risk of overturning because it frees the base constraint. It will have larger displacement, and many research also address the local failure problem. So based on this, we propose a numerical example of self-centering concentrically braced frame. We would like to see whether and to what extent the inerter is effective to control the rocking mode. This 10-story structure has 3 rocking surfaces at 5th, 2nd, and ground floor, with inerters and energy dissipators deployed at each rocking floor. And here is a response history of top story. In our interpretation, the rotation is directly referring to the rigid rocking mode, while the displacement is a combination of the rigid rocking mode and the lateral deformation of the structure members. So with the inertia, as you can see that the rocking mode is about fully suppressed after 10 seconds. After that point, the displacement response is fully contributed by the lateral deformation rather than the base rotation. And the flow acceleration is also reduced significantly. And the gap opening history shows that the rocking happens mostly at the ground floor. Level 2 has limited rocking behavior, and level 5 never rocks. This conforms with the records of the yield, the energy dissipator element. And here is the inertia behavior. Upper shows the velocity history of the structure and the inertias. And you can see the inertias are driven by the structure only. And the interaction between this inertia and structure is more like pulsive than a continuous effect. The inertia only engage with structure as this acceleration spikes. To gain a more comprehensive understanding of the effectiveness of the inertias in suppressing rocking structures, CSS assessment of the proposed structure is also conducted. And here, the same size and records and same settings are considered as Faridahs. Firstly, with the help of the MLF platform, the computational time is reduced by 50%. That's really efficient. And as we can see that the clutch inertia reduced the maximum inter-story drift in all range of the annual rate of exceedance. And additionally, I draw the response of the prediction, the response predicted by the sequential model. We can see that the sequential model overestimates the reduction effect of the inertia. The result of it is not conservative. And here's a conclusion. So firstly, the existing clashed inertia model cannot properly predict the seismic response of the structure and are prone to numerical chattering and instability. Secondly, a new modeling strategy. We propose a new modeling strategy using the MLF framework, and it has significant advantage in computational efficiency and robustness. The rocking structures minimize the residual displacement and damage, but lead to higher demands and risk of overturning. But the clutch inertia have a great potential to suppress these seismic demands. And currently, we are working on a large-scale shaking table test to validate the numerical model. And thank you for listening.
Okay, thank you very much. Thank you, Christian. Thank you, Faridah. Thank you, Yixuan. Thank you for all the interesting presentations. Now we're going to allow for some time for a Q&A session. Please feel free to type any questions you might have in the chat, or you can raise your hand and unmute your mic and ask any questions you might have. So I can't see any question in the chat. Can't see anybody asking something. I actually have a question myself, if you don't mind, and it's for Faridah. So I saw that you compare the different design codes, the Eurocodes and American standards, and I guess you design the different frames based on the different provisions, so the codes have different requirements. So can you let me know about the value of the utilization ratios based on the different goals? The utilization ratios for the frames when it comes to the design checks was like 80%, 90% of the design strength checks. Do you have this information?
So I just like design the frames based on the different design constraints from this from each seismic codes and compare them. Like, so I don't really specify the utilization ratio for that. So does that answer the question?
Yeah, I think what maybe if I can intervene here, I think what Evangelos is asking, Faridah, is about what is the percentage of strength that is mobilized in the design. So let's say you have a section that can resist, I don't know, 100%, and in reality, what is the actual value of actions that are going to that particular section? Probably we have not come up with those numbers. What we can say is that all the designs have been optimized by the same procedure. Maybe you can describe a bit the optimization procedure that we have used, Faridah. But we are basically comparing outputs of designs that are coming from exactly the same optimization procedure. So the highest, the most efficient sections we can find in the current catalogs. So maybe you can expand on that further.
Oh yeah, so the design process works in, so we have a database of steel frame sections, and then based on the design constraints of each course, which is the interstorageous limit, the capacity-based design, and the stability coefficient. So we start by trying the biggest section possible from the database of steel sections, sorry, and then we reduce it, we optimize it as small as possible to comply with those constraints of the design. So that's how it works. So yeah, we don't really check the utilization ratio thing, but it is like optimized based on the constraint of the each seismic code.
Okay, I see. Yeah, makes sense. Thank you very much. Thank you both.
Thank you.
I have a question. If I can?
Yes, of course. Yes, of course.
Yeah. If for all expositors, can you briefly explain to us the advantage of to use the conditional scenario spectra using too many scenario spectra ground motion instead only 44 ground motions like IDA procedure suggests, please?
Okay, so the one benefit of this CSS is that it can describe the hazard at the selected site. So with the IDA, where you scale the spectrum to reach certain structural response, actually it creates an unrealistic spectral shapes where it doesn't really consistent with the hazard at the selected site. So the benefit of the CSS is that your set of ground motion can describe the hazard at your site, like at your specific site. Hence that I mentioned that we use the site in Oakland so that the structure design in Oakland can be assessed with the hazard in Oakland. So that's the benefit of CSS. Yeah, we are aware that like we need a number of more analysis for that, but yeah, that's the price that we have to pay for the benefits.
Thank you.
Yes, thank you.
Thank you for your question, and thank you for the answer, Faridah. Let's wait a little bit more and see if anybody wants to ask anything else. Still can't see anything in the chat. I mean, as we wait, does anybody of you have any comments or like thoughts about upcoming work? What would you like to analyze in the future? What would you like to investigate more? I saw Yixuan, for example, he said you're going to proceed with some large-scale experimental testing. So are there any comments or thoughts about ongoing work or work that you like to complete in the future?
Yeah, now, for example, just speaking on that, Yixuan is at the moment designing a large-scale specimen, basically 3 stories of, in this case, a cross-laminated rocky system to be tested in the ISIS facility in North Macedonia as part of the IRIS European Access for Research Infrastructure Facilities project, right? And we are really looking forward to that because there is very little confirmation in general at the large scale of the response of inerters in structures. There is most of the experimental information and experimental research has been carried out at small scale level, right, or with buildings of a single story, and there is none absolute at all, none previous research looking at rocking structures combined with inerters. So, in a paper, I think it was 2019, with Rodrigo Thiers, we demonstrated that the inerter actually increases the frequency parameter of the rocking block. So basically what it means is that it makes a rocking block behave as if it was a larger block. And we know that larger blocks are inherently more stable than smaller blocks. So the inerter has that advantage without increasing masses significantly or anything like that. So it will be. We are really looking forward to that part of our, the experimental confirmation of everything that we've said in the last few years. And yeah, and I think that the point that you made about the percentage of utilization ratios, I think it's something that we should calculate as well, Faridah, just to include in our drafts. Yeah. But I don't know if anybody has anything else to add.
I do have any future work. I already submitted my thesis.
I see. Yeah. Good luck.
Thank you.
Okay. Thank you very much. Again, I still can't see any question. Type in the chat. Just gonna give a last chance to our audience to see if anybody wants to maybe unmute their mic and ask any question they might have. Okay, I can't see anybody. I can't see any hands raised. Anything on chat? Okay, then I guess we can conclude today's lunchtime webinar. Thank you very much for accepting our invitation to present on behalf of Second Young Member Subcommittee, and I hope you continue doing all this interesting work in the future as well. Good luck with everything. Thank you very much. And thanks for everybody for joining us today. Thank you.
Thank you very much. Thank you,
Thank
Evangelos.
you.
Yeah, thanks to
Thank
you.
you very much.
Thanks a lot.
Take care. Have a nice day.
You too. Have a nice day.